Thank you. Let's see. So thank you to ILSI for the invitation to speak. And like the others, I will give my disclosures. So I do receive funding from the USDA as well as restricted and unrestricted gifts from a number of food companies. And I also consult for a couple of companies or associations within the flavor industry. So with that said, I'm going to talk about sensory properties and how those sensory properties of foods contribute to food choices. So why we're here, we all know. Many processed foods contain high levels of sugar and salt, and with the Western diet, these have started to result in health issues related to obesity, to cardiovascular issues, metabolic syndrome, and so forth. And many of the healthy foods that are low in sugar and low in salt, which in theory would be excellent foods to consume, happen to also be high in bitterness. And so, as we've heard from Gary and as we've heard from John, there's this innate sort of avoidance of these types of foods due to this presumed bitterness. In America and in a lot of Western countries, the reality is that we're time poor, right? We have a lot of things going on in our lives. We're trying to multitask and balance multiple things in our environments. And the reality is that most of us don't have the time to really grow our own foods and take the opportunities to perhaps make all of our meals in the healthiest of ways. So the reality is that processed foods are going to be a component of our meals and in our society. And so I think the reality of what we're looking at is that it's not so much that we need to try to eliminate these types of processed foods, but in fact, we need to figure out how to make them a healthier, better alternative. And in fact, there's hope because it does seem like Americans are hearing the message, right? So 6 out of 10 shoppers, as they're choosing their foods, look at calories, look at levels of fat, look at levels of sugar in foods in informing their choice. Now, obviously, they're not always making the best choices, but at least the message is being heard, and I think that's promising. So I think the trick for the food industry is to make these healthier foods more rewarding. So how can we give consumers better options that are healthier, but that are just as rewarding and just as fulfilling as the full fat, full sugar, full salt types of foods? So, as Gary had alluded to in his talk, we know that a variety of senses are involved in the consumption and perception of foods. So we know water-soluble chemicals are detected by the taste pathway. And we know that the volatile chemicals, so the flavor compounds, those aromas that are associated with flavors, are detected by our aroma or our olfactory pathways. But we also know that other types of sensations also contribute to our food liking and our food choices. So the touch, which is obviously involved in texture perception, as well as temperature and some of these kinesthetic sensations that Gary had described earlier. Vision is also very important. The hue, the color, the form that those foods have inform expectations and inform in terms of what we're thinking those foods might taste like. And then even audition, right? So the crunch that's associated with the textures of foods, or the carbonation that you hear when you open a bottle of soda, for instance, or carbonated water. So I'm going to focus my talk primarily on taste, with a specific sort of focus on salt and sugar, because that's of interest for the thesis that we're trying to address here. And I'm also going to talk a little bit about potential opportunities for using olfactory and flavor types of strategies to reduce some of those sugar and salts in foods. So we know that flavor is important to food. And we know that taste in particular is a key determinant of product acceptance. But as we sort of alluded to earlier today, not everyone is created equal, right? So there's not one single strategy that can be applied across the globe or the nation to reduce sugar or salt in people's diets. So what this graph shows, for instance, is that there's a large cluster of people. Whoops, wrong way. Whoops, now what I do. Okay, well, I don't know where the... So on the left, what we see is a cluster of people. This is concentration, sucrose concentration on the bottom axis, and standardized liking. And as you can see, there's a cluster of people that like low concentrations of sugars, okay? So their optimal sweetness is associated with sort of a lower concentration of sugar. And then there's people that like really high concentrations of sugar. And so they prefer really sweet foods. And so again, with these two different clusters of people, these two different ways that people are sort of preferring different types of foods and optimal profiles, we have to have different types of strategies. And we also know that in some cases, bitter can also be a positive attribute associated with products. So for instance, in beer, there is an ideal level of bitterness in beer. There is an ideal level of bitterness in coffee. And so we believe that bitterness liking tends to be a learned effect. In the case of particularly beer and coffee, that learned effect is probably associated with the pharmacological aspects that are associated with the caffeine or the alcohol that are in those products. But I think that it's sort of a misnomer to say that we always avoid bitter, because I think there are products that bitterness is sought after. So, how might we go about reducing the amount of sugar and salt in foods? And so there's been some historical approaches that I'm going to talk about, and then there's been some more recent approaches that companies are sort of trying to undertake to reduce these compounds. And then ultimately we'll talk about a couple of potentially newer strategies that sort of change the way that we might be able to approach this. So I'm going to start with sodium reduction. Okay, so sodium reduction is essentially one of two strategies that companies might be able to do to reduce the amount of sodium in their foods. So with sodium reduction, we're essentially talking about the removal of salt, okay, or the removal of sodium from the product. So how much sodium can be removed from a product is matrix dependent. And so what this graph shows is that with fairly simple models or with fairly simple foods, you can't take very much salt out before people notice. However, as the matrix gets more complex, you can remove more salt before people notice. So on the left, on the y-axis is the just noticeable difference, okay? So this is the amount of salt that people can remove before you just notice a difference, okay? So in the case of soup and cheese sauce, you can remove around 15% of the sodium chloride before people notice. So on the one hand, that sounds great, right? So you can remove that amount of sodium chloride, people don't notice, so we have a sodium reduction. The reality, though, is that the magnitude of that salt reduction is still relatively small. So in the case of soup, this was essentially a 51, so that 15% sodium reduction was a 51 milligram reduction, okay? And in the case of the cheese sauce, it was a 150 milligram reduction before people could notice it. So on the one hand, that's great. We can reduce the sodium before people notice, but when we put it in the context of how much sodium the average American has to remove from their diet, it's sort of a drop in the bucket. So the average American has to remove roughly around 1,100, 1,300 milligrams of sodium. So if we're doing that at 50 milligrams at a time, we got a lot of drops that we have to fill that bucket up with. But there is some hope, right? Because there is a certain amount of sodium that can be removed before people even notice a difference. So what happens when they do notice a difference? Well, probably unsurprisingly, when you notice a difference, people don't like the product anymore. So what this graph shows is these are both motivated and unmotivated consumers. So the motivated consumers were people that had some health issue related to sodium that they were sort of motivated to remove sodium for their diet, and the unmotivated people are, people that don't care, right? And so what happened in this particular study is this was tomato juice, and so the tomato juice was given to the cohort of people for 3 weeks, okay? And then at week 3, they removed about 500 milligrams. So it went from 650 milligrams to around 150 milligrams of salt in that juice. So a big reduction, and it was obviously very noticeable. And you can see there was a precipitous drop in liking, right? So, on the one hand, in sort of a normal behavioral sort of paradigm where people are going and choosing foods and consuming foods in the grocery store, if you've experienced this product where you take it home and you evaluate it and you have this massive sensory change and you don't like it, the likelihood that you're going to go and purchase it again is small, right? But again, there is some hope here because as you can see, in this particular case, these people were sort of forced to continue to consume it, right? And so as they continued to consume it, their liking for those products tended to rebound, okay? So exposure to these low sodium products that they may not like initially might be able to be overcome with, again, this repeated exposure. So, we've talked a number of reasons why that liking might decrease. So obviously just the decrease of sodium. As sodium, that salt taste, that salt sensation is appetitive. We like it, okay? So when we remove that, has a negative influence on our liking. And as John and Gary had talked about in their talks, sodium is also a great bitter blocker, right? So with the removal of sodium, we have perhaps an increase in this bitterness, and then with certain products, that increased bitterness is then detected, and people start to dislike that product and search for things that have, again, that higher sodium content, okay? So sodium reduction is one way to approach this, right? Simply removing sodium in hopes that people don't detect it, because once they detect it, there seems to be a breaking point where they'll no longer consume the product. Another approach is sodium replacement. So replacing sodium with something else that's potentially salty. So as Gary said, for sweet compounds, there's a lot of different compounds that are inherently sweet, that taste sweet. For saltiness, we're really, really restricted. So lithium chloride or potassium chloride. And as Gary alluded to as well, potassium chloride has some baggage that's associated with it. So a lot of people detect either a bitterness or a metallic sort of sensation that's associated with it. So as you're removing salt and you're adding potassium chloride into that product, you're introducing some negative sensory attributes that will ultimately potentially decrease liking for that product. So this is a strategy that's been used, and it's been used relatively successfully in products, for instance, like soup, where in some cases very high levels of sodium, and you can reduce those in some cases 50%, replace it with potassium chloride, and have a significantly reduced product that still has some level of saltiness that's consistent with the full salt product. So again, how much salt can be replaced? How much KCl can be reintroduced in the product where the sodium's being removed? It's matrix dependent. And again, the more complex that matrix is, the more complex that food is, the more potassium chloride you can use to replace the sodium chloride. And so for more complex types of products like cheeses and meats, there's an opportunity to actually pull out a significant proportion of that sodium chloride and reintroduce potassium chloride without necessarily having a significant impact on either the salty perception or the liking. But what happens as you add more and more more and more potassium chloride? This is a nice figure because it shows sort of the dual effects. So certainly on the one hand, as you add more potassium chloride, the saltiness increases. But as you can see on the figure on the left, figure A, the bitterness also increases And it's this bitterness that is sort of the limiting factor with removing sodium chloride and adding potassium chloride into those products. So it should be said, however, that this effect is sort of dependent on a lot of things. So it's dependent on the matrix, it's dependent on the food, but it's also dependent on individuals. And there's a lot of variability in the sensitivity that people have to this bitterness or to these metallic tastes. So not everybody, again, is created equally. And so some people tend to be more sensitive to it, some people tend to be less sensitive to it. And I think trying to understand that better will certainly help improve the strategies that companies can use to replace salt with potassium chloride. And, as you can imagine, as potassium chloride increases, the perceived bitterness increases, and as a consequence, liking decreases. And again, this tends to be product specific, and some products are more amenable to the potassium chloride replacement, and so this strategy is potentially more successful in those types of products. Okay, so I'm going to switch to sugar, and there's basically two strategies that are very similar, sugar replacement and sugar reduction. So sugar replacement is what we're probably most familiar with because this is sort of the approach that many companies have taken historically. And so the idea was to replace sugar or high fructose corn syrup with a variety of other compounds that taste sweet. And so we have the diet versions of certain products where sometimes it may be an aspartame type of a product or sweetener. We also see products where now there are specific sweeteners that are sort of highlighted. So, carbonated beverage with Splenda or with sucralose, okay? So a different become more prominent. We also know that the temporal profiles of the sweetness of these artificial sweeteners or these non-caloric sweeteners don't match that of sugar. And so oftentimes consumers will complain of a lack of an upfront sweetness or of a lingering sweetness associated with these artificial sweeteners that they don't like because it doesn't match the sugary temporal profile that they're used to. And so this is an area where a lot of food companies are spending a lot of time trying to match the temporal profiles of sugar by doing different blends and by looking at different ways of trying to increase that upfront sweetness and cutting off some of that lingering sweetness. We also know that sugar reduction impacts mouthfeel. Okay? So these sugary beverages with lots of sugar or carbohydrate in them tend to be thicker. So they have a mouth coating, a body that's associated with them. And as we remove that carbohydrate and replace it with artificial sweeteners or non-caloric sweeteners at very low concentrations, we lose that viscosity, we lose that mouthfeel. And again, that's perceived as a negative attribute by a lot of consumers. And so in this slide, you can see those products that are high in mouth coating and body are the ones that have sugar, and the compounds that are the products that are diet, that are low in sugar, are low also in mouthfeel and body and these sort of attributes that are important to the textural elements. And it just so happens that people, on average, although there's a large variability in viscosity perception, people on average can detect the difference in viscosity between a mid-cal and a regular beverage. Okay, so that removal of that sugar results in a viscosity difference that people can detect. And so it's a real sensory component that companies are having to deal with. Similarly with bitter reduction, so there's now been a lot of functional products where a lot of these compounds that have high health benefits are being put into products, and they're having to figure out ways of masking or reducing that bitterness. And so there's, again, been a variety of strategies. So one strategy has been sort of this generalized masking strategy. So there's been products like beta-cyclodextrin, homerodiacetyl, and CMC. So CMC is a thickener, so it reduces the ability of the bitter compounds to be able to actually reach the receptor. These other compounds seem to have or have historically been said to have sort of this generalized bitter blocking or bitter masking association, but as you can see on the graph on the right, it sort of depends on the product, it depends on how the concentrations are being used. So more recent approaches have been looking at aroma interactions. So one approach has been to try to take advantage of these learned opportunities or these learned experiences of pairing flavors with specific tastes. And so you can see that, again, that there's been some success. So there's been some food odors that, if added to certain types of products, will enhance the sweetness or enhance the saltiness. On the right, we see citolin and furfuryl acids, or furfuryl thiol. These are roasted types of aromas. And so when you add these aroma compounds to solutions of sodium chloride, we can increase that perception of saltiness. And again, when you add things like maltol or strawberry flavor to sucrose solutions, you can increase the perception of sweetness. However, it depends on how people evaluate it. So consumers evaluate this in what we call a synthetic way, right? So they're not breaking the attributes down into component parts. So when we break those attributes into component parts, for instance, using a taste panel or a taste expert who sort of looks at the various attributes that are associated with the product, that sweetness sort of, those enhancement effects sort of decrease. So more recently, there's been targeted modulation, so using cell-based assays, very similar to what's used in the pharma industry to identify PAMs, or positive allosteric modulators, or NAMs, negative allosteric modulators, to identify specific compounds that activate or antagonize very specific receptors. And so in the case of PAMs, we can increase the efficacy or the potency of the particular receptor, so we can make it respond to sweeteners at lower levels, or we can make it respond to a sweetener with a higher response. In the case of NAMs, we can block those responses. And in fact, there's been some products that have been identified that actually have had some commercial success. So in the case of enhancement, on the left, you can see, if you the far right bars on that left-hand graph, you can see that the compound in and of itself doesn't have any taste quality. However, when you add it to sugar, you can see that it increases the perception of, or this is a cell-based assay, so it increases that cellular response to the sweetener 100%. Okay, so this is a true allosteric enhancer. Okay. There's a variety of other compounds that have been identified that are called agoallosteric enhancers. So they do have some agonist activity at certain levels, so they are sweet. But when you add them, and these are shown on the left of that graph, so when you add them to a sweetener, they enhance the sweetness more than the little bit of sweetness that you're adding. So you're getting more bang for your buck. And similarly, we've seen things on the antagonism side as well. So we've been able to identify compounds that block specific bitter receptors that are responsive to the bitterness of ACE-K. And we can see that in taking those same compounds that were used in that cell-based assay, we can see the same effects sensorially in humans. So we can reduce, in this case, by about 50% the perceived bitterness that's associated with that ACE-K. So again, it's not so easy just to remove these salt and sugar, as we've talked about before. So sugar and salt have a lot of functional properties beyond just the sensory properties that they bring. Sugar is used as a bulking agent, a humectant. It adds color from the Maillard reactions. It's used as a preservation, freezing point reduction. So it has a lot of functional properties beyond just the sensorial component that it brings. So simply removing it will impact all of these other functional aspects, and it makes formulation much more difficult. It's also important to identify, or to, I guess, specify that a lot of these compounds that are being identified for use as replacers or enhancers or modifiers have to actually have very low cost in use. And this is a huge hurdle for a lot of these suppliers, because refined sugar is anywhere from about 15 to 25 cents per pound. Okay, so these compounds that you're squeezing out of a plant or that you're identifying that have these effects have to have that same level of cost and use. And similarly with salt. So anything that's going to be used to enhance the saltiness also has to be at a low cost in use. So very quickly, the last two strategies that I'm going to talk about are sort of emerging strategies. So one is this idea of kokumi, and as you'll see, this idea of kokumi, it's kind of in maybe about the last 5 or 10 years sort of started to getting some attention. But the way it's described is very similar to what the description of the original umami compounds were. So it has an impact on the thickness or the continuity or the mouthfulness of products. These tend to be these small peptides, these tripeptides, and when added to products, they seem to have an effect both on a variety of different sensations like sweetness and saltiness, but they also have a larger overall effect on the quality, if you will, or the character of those flavors in the solutions that they're being added to. So this might be an approach to sort of improve the quality of products where we've removed sugar or salt by adding these types of compounds. And that leads me to my final slide, which John alluded to in his work as well, or in his talk as well. So historically, companies have really been focused on trying to match the sensory properties of their products to their full sugar or full salt versions. And the reality is that's really, really hard. We don't have the tools to do that. Another approach where the target's bigger is to actually focus on trying to make products equally tasty, equally rewarding, equally liked. There's a lot of ways to do that, right? It's very hard to match a specific sensory target, but there's a lot of ways to make something liked. And perhaps that's a better strategy in the long run. And with that, thank you.
Thank you, Chris. So I think we have time for one question. Otherwise, we can handle most of this during the panel discussion.
Yep.
Do we have one question? Could fight over it. Sorry.
Hi, my name's Beth Skoraki. I'm press. I'm with Lifehacker. And I had a question based on my personal experience. So when I was a kid, I couldn't drink Diet Coke. It tasted so bitter to me, like so unbelievably bitter. And then at some point I decided I wanted to drink this, and I got used to it and sort of trained myself, and now I can't tell the difference anymore between like regular and diet. I can't taste that bitterness, or it's very hard to taste. I'm curious if there's a reason for that, and if you can talk a little bit about like the sweet and bitter interaction.
Yeah, so I think similar to the question that was asked after John's talk. So I think there's kind of two elements to that. So it could be that you, as opposed to not being able to tell a sensory difference, that you just effectively you like them both, right? Or you like them now. Actually, probably the diet product even more. Yeah. So so how that might, I think there's a lot of speculation in terms of how that might occur, where you've actually reduced sensitivity. Certainly with ongoing, exposure to these types of products, our sensitivity changes, but I don't know that it's been specifically looked at in those types of products.
Great. Thank you very much.